Hello and welcome to the section on complex numbers, imaginary numbers. Where did they come from? Why do we use them? Great questions. This is one of the most exciting days in all of mathdom. Here we have three equations that almost look, well, they look very similar, but they're all worlds apart. Let's start with this one. X squared equals 9. Back in chapter 5, we were able to take this one and go x squared minus 9 equals 0. And factor this, it's a difference of squares, and you get x plus 3, x minus 3, and that equals 0. Set this guy equal to 0, you get x equals negative 3, and x equals a positive 3. Notice that these numbers are nice. This one's a natural number. This one's an integer. They're both integers. And it was kind of nice because this was a perfect square. And you can kind of see how that works. What squared equals 9? Well, 3 does. You would square root it. You get 9. But it also, we got all of the answers by factoring. Well, here you can see that just looking at it, what squared would equal 7? You would have to go backwards and do square root of 7. It also, negative square root of 7 would also work, but just looking at this number, notice that this is now an irrational number. Based on what number we put over there, number squared to equal 7, square roots that don't come out nice were called irrational. Well, this one creates a huge problem. Even though it looks nice and soft, everything, x squared equals negative 1. Ooh, think about those. X squared equals negative 1. Is anything squared going to equal a negative number? There isn't a real answer. And that's what you have to do. No real answer. And what do you mean no real answer? Well, if you remember on the real number line, we first started out with their 0 and 1, 2, 3, 4 natural numbers, whole number, integers down here, and then we filled in all the gaps with fractions, all the rational numbers. And then the irrational numbers, there were still holes left, and so here's where we get this. And so like the square root of 7 is one of these that fills in the holes, and so we get all the real numbers there. However, now we run into a thing where here are the negative numbers, and negative numbers squared can never equal a negative number. Positive numbers squared always equal positive number. 0. Yeah, this answer is nowhere in there. We would love it to be the square root of negative 1, but it's not a real answer. And so that's the thing about real, is this double line. We don't have it on the number line. So like all good mathematicians, we found a way out of it. We said, you know what? Let's make up a number called the square root of negative 1. And he's imaginary. He's not real. And so he's not anywhere on the real number line. He's off somewhere else. We call him I. Yeah, so this makes us have I squared is negative 1. And this is the weirdest little thing we've ever done. And at this moment, usually students look at me like, are you kidding me? You just made up an answer to something that couldn't be solved. Yeah, we kind of did. Turns out that this thing does have some value, and this is one of the greatest mathematical discoveries ever. So we're going to pause for just a minute while you see this I squared equals negative 1, and we're going to talk a little bit about the history of math and some of the leaps that have been made that help us to get there. Here we have a quote by Albert Einstein that talks about some of the greatest discoveries ever. It says, "The mind can proceed only so far upon what it knows and can prove. There comes a point where the mind takes a leap, call it intuition or what you will, and comes out on a higher plane of knowledge, but can never prove how it got there. All great discoveries have involved such a leap." Fascinating. He talks about this intuition. Now, he wasn't one for organized religion, didn't talk a lot about God, but he always had this sense that there was something bigger than himself in nature. And so we have a very similar thing in the scriptures. Here's one, D&C 88, verses 77 through 79. "And I give unto you a commandment that you shall teach one another the doctrine of the kingdom. Teach ye diligently, and my grace shall attend you, that you may be instructed more perfectly in theory, in principle, in doctrine, in law of the gospel." Talking about those that teach the gospel being instructed more perfectly. And notice that it lists out a few subjects here of things both in heaven and in earth and under the earth, things which have been, things which are, things which must shortly come to pass, things which are at home, things which are abroad, wars and perplexities of nations. Elder Bednar at BYU I gave a talk and it says, hey, this applies to all aspects of life. And throughout all the history of math, much like what Einstein said, we've had these great leaps and these great discoveries that nobody saw the value of until much, much later. And so we can't go very far without applying this to your own lives. In True to the Faith, under Revelation, this is this excerpt. You have the ability to pray for guidance in your own life, not just with cool math discoveries, but with everything in your life. The Lord said, ask and it shall be given unto you, seek and ye shall find, knock and it shall be opened unto you. For everyone that asketh receiveth, and he that seeketh findeth, and to him that knocketh it shall be opened. In order to find and receive, you must seek and ask. If you do not knock, praying to your Heavenly Father for guidance, the door of revelation will not be open to you. But if you approach your Father in humble prayer, you can eventually receive revelation upon revelation, knowledge upon knowledge. And that's a promise given to everyone. All right, that was a good digression. Yeah, these inspirations, these discoveries that were made in math were leaps that sometimes the discoverers themselves didn't understand, and you have that same promise. And to answer your question, yes, this does become valuable later on. The arithmetic of I, and what we'll discover in this section, is incredibly valuable when solving problems involving electricity and magnetism. The magnetic fields that are generated around electric currents, called electrodynamics. That whole field of study, the arithmetic of the imaginary numbers, the complex number system, is actually incredibly valuable there. Okay, let's continue on talking about this newfound I. Notice what happens. If we understand that I squared equals -1, it's a strange bird. When you square it, it gets a -1, but this is a normal, real, rational integer that's nice. Let's see how some of this works. If we take 4i times 4i, that gives us 4 times 4 is 16i squared. This acts just like a variable. 16i squared, what is I squared? -1. This is -16. So that means that the square root of -16 is 4i. We've never been able to do that before. Take the square root of negative numbers. So yeah, what do you think the square root of 25i is? That's right. Oh, not the square root of 25i. Let's not do that. That's not so good. The square root of -25 would be 5i. The square root of 36 -36, that's going to be 6i. Because when you times it by itself, 6i times 6i, we get 36i squared. And what is I squared? It is -1, that makes that a -36. Kind of a strange little animal, but this right here is what you always have to remember. The I squared is -1. Now we need to remind you of something. On our number systems, we just created a whole new number. So remember we started off with like the natural numbers way back, and this was 1, 2, 3, 4, 5. Then we added to that the 0, and we got the whole numbers. And then we added to that, what did we add to that? Oh, all the negatives. And we called them the integers. Does this bring back nice, warm, happy memories? And then we added all of the fractions. So all the fractions and everything together became known as the rational numbers. Then we added, whoa, all of the irrationals. And together the rationals and the irrationals out here, that became the real numbers. Yeah, so the irrationals are sitting over here. The rationals break down into those guys, and they like nest themselves. Okay, now these numbers with i's in them are considered purely imaginary. And we'll use an im to represent that. So that would be like 4i, 5i, 6i, I. Those are all imaginary. And so together, all the imaginaries and all the reals together form what is called the complex numbers. So like this, complex. Oops, just with one line there, that's fine. A double-lined C, and it is complex. And so they would be numbers like 2 plus 3i, or 2 minus 3i, or something like that. So let's clear this off and see what happens with our newfound numbers. Let's try a few of them and see what happens. I is I. This is the square root of -1. I squared is -1. What this actually means is that you will never see, or in simplified answers, you'll never have I to any power greater than 1. I'll show you what I mean. I cubed. Well, this is I times I times I. And what is I squared? That's a -1. So this is really I squared times I. So that's -1 times I is I. I cubed and negative I are the exact same thing. Let's do I to the 4th. Well, that's I squared times I squared, right? 2 plus 2 would give us 4. Well, that's -1 times a -1. That's a +1. I to the 4th is 1. We could keep going. Let's do like I to the 5th. Now, every I squared is going to be a -1. So let's break them up into things of 2. I squared times I squared, that's 2 plus 2, that's only 4. We have an extra one there. So I to the 5th would be I squared times I, which would be -1 times -1 times I is I. I to the 5th is I. Let's do something bigger, like I to the 13th power. Now, we know I squared is -1. So how many of these would it take to get as close to 13 as possible? Well, if you take 6 of them, 2 times 6 will give you 12, and then you'll have one I sitting out by his lonesome. So I squared to the 6th power, that's I to the 12th, and then there will be one more I to make I to the 13th. Well, that becomes, what's I squared? -1. It's -1 to the 6th times I equals, what's -1 to the 6th? 1. 1 times I is I. Ooh, let's do an even bigger one. Do you think we can get one really big? I to the 18th power. That's not huge. This is an even number, and you can see it's I squared to the 9th power. No people left over, no I's left over, so that becomes -1 to the 9th power. Now, negative to the 9th power would end up with a negative. That's going to be a -1. Do you see how everything I's above the power of, well, even the power of 2 always reduce down to something that's nicer? -I, 1, I, or 1. All right, so let's do a really big one, like I to the 425th power. Now, this is an odd number, so let's see how many I squareds we can get out of it, first of all. So I squared to the, let me see, if we divide this by 2, it's 212, right? 2 times 212 is 424. There's 424 of the I's, and we have 1 left over. So -1, that's I squared. And you should always repeat that. I squared. What is I squared? -1. What's I squared? -1. And so here we go to the 212th power and 1 extra I. -1 to the 212th power. Negative times negative times negative 212 times, that will be an even number. No, it's an even amount of negatives, which means it's +1 times I is I. See how that kind of works? That's pretty snappy right there. Alrighty then. We should note up here on this number line, I right here is not negative, it's not positive, and it's not 0. It turns out to be up here. And you will not be tested on this, but they actually put an entire axis here called the imaginary number. So imaginaries go up here. And so if you have a number like 2 plus 3i, they would go 2 plus 3i. So imaginaries look like 3i. Complex numbers look like this. And they will always look like a plus bi. They have a real number and an imaginary number. So the purely imaginary numbers like 3i actually look like 0 plus 3i. They just have a 0 real part. And the purely real numbers, like our good old friend like 7, would be like 7 plus 0i. And that's okay, they just mean the exact same thing, but this is a standard form for a complex number to be written on. And complex numbers include everything that we've ever done, all of these numbers, the irrational ones, the ugly ones, and the newly found imaginary ones. So let's try a few for you. To the boards! Here are some problems for you to give a shot, and pause the video, write them down, and go ahead and give them a try, and unpause the video, press play again when you're ready to move on. Excellent, welcome back. I hope you had a good time. -9, square root of -9 is going to be a 3i, because when you take 3i times 3i, the I squareds become the negative. Very good. Ooh, square root of -20. Now in this case, the -1 is going to be an I. 20, is there a perfect square that we can simplify out of there? Yeah, this was 4 times 5. So that becomes your I, that becomes a 2, and then the square root of 5 has to stay there. So we simplify it, but every negative root can simplify. So this is a purely imaginary number, and yeah, it's got irrational in there, but that's all right. Next, times these two together and you get 35i squared. Well, that's I squared is a -1, so this is -35. I to the 15th power. Well, that would be I squared. That's what we know. How many of those can we get? 2, 4, 6, 8, 10, 12, 14. So 7 of them. And then we have 1 left over. This is I to the 15th. Okay, so this guy is -1 to the 7th times I. -1 to the 7th power, that's 7 negatives all times together, so that's negative I. I to the 15th equals -I. And then the last one, I to the 246th power. That's going to equal I to squared how many times? Looks like 123 times. Is that right? And do we have any remainder on that at all? 2 goes into 246, 123 times. No remainder. So this is going to be -1 to the 123rd power. That is an odd number of negatives. So we come out with -1. I to the 246th power is -1. Nice job. All right, so we found out what I is, the imaginary unit. We found out the complex numbers where you have imaginary and real parts, and we did powers. So we actually did all 3 of those. Now we need to know how to add, subtract, multiply, and divide them. So nice and easy on this one. If we go 2 plus 3i and we add this to say 5 minus 8i, notice we've got 2 complex numbers here, a real and imaginary part. And what's nice about this is it's exactly what you've done before. I'm going to put it right down here. The real parts add, and then 3i minus 8i, that's minus 5i. That's exactly how addition works. Let's make sure we can do subtraction. 4 plus 8i minus 7 minus 3i. Let's do something like that. As you would hope, i's work exactly like the variables and the square roots we've done before. The negative jumps in and we have 4 plus 8i minus 7 plus 3i. And we just put them together. This becomes 4 minus 7 is a -3 plus 8i plus 3i is plus 11i. And that's the answer. Addition and subtraction, check. Multiplication also works just the same as you've been doing previously. 2 plus 3i times 4 minus 7i. Here we have 2 complex numbers timesing. Yeah, you just times like normal. Go ahead and jump that guy in. You get 8 minus 14i. That becomes plus 12i. And then minus 21i squared. And the only thing that's different is I squared always becomes what? -1. That's right. So this actually becomes plus 21. So that minus a minus here, that negative minus a minus 21 makes that a, let's get rid of that, plus 21. So 8 plus 21 is 29. And then minus 14i plus 12i, that's minus 2i. Oh, look at that. Was that nice or what? Let's do it one more where we only do a distributive, like 3i jumping into -5 plus 7i, something like that. This one would just distribute like normal, like you had an x there instead, and you get -15i, and then you have plus 21i squared. And what is I squared? It's -1 indeed. So that's really a minus 21. So -15i minus 21, they normally write it in a plus bi form. So with the real number here, and then the imaginary number, minus 15i. Real number, imaginary number. And you'll never have an I squared or an I cubed in any of your answers because they'll always reduce down. Excellent. All right, so that's addition, subtraction, multiplication. Now division. This is an unusual, this one is the weirdest of all of them. So if I had something like 7 divided by 3i, I want you to look at this problem and remember that I came into being as the square root of -1. So if we were to have something like 7 over 3 square roots of 5, I want you to remember, how would you do this problem? Let's divide this off so we can do division over here. How would you do this? Well, you don't really divide, you rationalize the denominator when you times by square root of 5 and square root of 5. And the whole goal here was to take 7 square roots of 5 over 3 times, what's square root of 5 times square root of 5? 5. And we didn't have a square root left because when we times them, the square root of 5 times the square root of 5, it left the irrational world and became rational. Square root of 5 times square root of 5 was 5. So we got 7 square roots of 5 over 3 times 5 is 15. So this here, the exact same thing takes place. This is the square root of -1. So we're going to times it by something that'll allow it to get out of its imaginary world on the bottom. So this becomes 7i over 3i times I is 3i squared. What's I squared? That's right. It is -1. So this is 7i over 3 times a -1. That's a -3. So you'd write it just as -7/3 I or -7i over 3. Either one of those is great. We could have something even bigger. Let's try this one. 2 plus 3i over 5i. Something like that. Well, you're going to do exactly that. You're going to, just what we did before, you've got to times the top and bottom by I. And what does that do for you? I times I will get out of the imaginary world. So this is going to be 2i plus 3i squared. See how that just distributed in like that? Good. And then this becomes 5i squared. What's I squared? That's a -1. So it becomes, ooh, there's another I squared, -3. So -3 plus 2i over -5. Now, if we write this in appropriate format, this is -3 over -5, which would be 3/5. And then 2 over -5 is minus 2/5 I. Excellent. And for the last one, let's try one a little bit tougher. 2 plus 5i over 3 minus 4i. Something like that. Okay, so on this one, now remember what we would have to do is not times by 3 minus 4i. Back when we did the square roots, there was a trick. We had to use what was called their conjugate, the 3 plus 4i. Does that ring a bell? Putting in the minus and the plus, because what happens when we times them? Well, let's do it and find out. Let's do the top first. Let's see what we get. 2 times 3 is 6. 2 times 4i, that's plus 8i. 5i times 3, that's plus 15i. And 5i times 4i is plus 20i squared. And I squared, we know, is minus 20. Okay, now let's look at the bottom and see what happens. 3 times 3 is 9. And 3 times a plus 4i is plus 12i. Negative 4i times 3 is a negative 12i. There's the magic of the difference of squares. And then minus 4i times plus 4i is a minus 16i squared. Let's take care of these. And just note, I squared becomes a -1. So this is minus a minus 16. That's plus 16. But those go away. That's what's the power of, let's write this down, conjugates. That's what conjugates do. When you have a plus in one side and a minus in the other, when you times them as binomials, the middle terms cancel. And notice that we have no i's now in the denominator. So we end up with 6 minus 20. So that's a -14. And then 8i and 15i is 23i over 9 plus 16.
That'll give you a 25 on the bottom, and then you write that in the official format of a plus bi. It's negative 14 over 25 plus 23 over 25i.
Whew! Okay, time for you to try a few.
To the boards!
Here you go. Write these down in your video notebook. Give them a try and be sure to press play when you're ready to resume. Welcome back. The first one, we have subtraction, which means we just jump that in, and we have 5 plus 3i plus 4 minus 7i. And what happens there? We have 5 and 4 is 9, plus 3i minus 7i is minus 4i. Nice, I like the subtraction ones. Number 2, multiplication, where the 4i just jumps in and we have 12i plus 28i squared. I squared is negative 1. So that's 12i minus 28. So if we wrote it in the official form, it would be negative 28 plus 12i. They're the same thing if you write 12i minus 28, but this is the a plus bi form. All right, multiplication with binomials. Jump that over and we get 6 plus 14i minus 15i and minus 35i squared. What is I squared? I squared is negative 1. So let's put a plus there. So we get 6 plus 35 is 41. 14 minus 15i, that's a minus I. All good. Let's circle those. And the bottom ones. All right, this is division, which means we're just really rationalizing the denominator or realizing the denominator. Is that a word? I don't know. We're going to times by I and times by I. So on the top we get 5i plus 6i squared over 7i squared. Let's take the I squareds, become negative 1, negative 1. And so we end up with negative 6 plus 5i all over negative 7. So writing that in official form, negative 6 over negative 7 would be 6 sevenths minus 5 sevenths I. And it could be written in either way. That's perfectly fine, either one of those. All right, the last one, number 5. This is a binomial on the bottom, so we have to times by its conjugate, which is 4 plus 5i. So that is what we're going to be timesing by, 4 plus 5i on top and bottom to get rid of any i's on the bottom. So 2 times 4, that's 8 plus 10i plus 12i. And then the 3, that's what, plus 15i squared all over. 4 times 4 is 16. 4 times 5, that's the plus 20i. He's going to go away. Minus 20i, there's the guy that takes him out. And then minus 5i times plus 5i is a negative 25i squared. Let's take care of all the I squareds. That becomes a negative 15, and that becomes a positive 25. Good. And then so 8 and a negative 15, that's a negative 7 plus 22i all over. 16 plus 25 is a 41, and that guy are gone. So 41. So negative 7 over 41 plus 22 over 41i, and nothing really reduces. So there's our answer. Nice job.